Hello, everyone. Last week, we talked about principles of the deadlock, and then we went through 3 different methodologies of handling deadlock, including deadlock prevention, deadlock avoidance, deadlock detection, and we also talked about the integrated deadlock strategy. In this week, the lecture is divided over 2 parts. In part 1, I will talk about the dining philosopher's problem and how this problem actually provide a good example for deadlock and synchronization and how this could be solved using either semaphores and monitors. And then I will address the concurrency mechanisms in different operating systems, including Unix and Linux, Solaris, Windows, and even Android. Now let's start the dining philosopher problem. We now turn to the dining philosopher problem, which include 5 philosophers who live in a house where a table is laid for them. So you can see in this picture, we have a table where we have philosopher 1 as an example, and a 2 and a 3, a 4 and a 5, like just 5 philosophers who are just living in the same house. And then they would like to have a dinner on a table. The life for each philosopher consists principally of thinking and eating. And through years of thought, all of the philosophers had agreed that the only food that contributed to their thinking efforts was spaghetti. That's funny. Due to a lack of manual skill, each philosopher required 2 forks to eat spaghettis. The eating arrangements is very simple. Around the table on which is set a large serving bowl of spaghetti. So we can see the bowl of the spaghetti here. And we have 5 plates also for each, 1 plate for each philosopher. 1 for each philosopher, and we also have 5 forks. A philosopher who is wishing to eat will go to his or her assigned place at the table, and then using the 2 forks on each side of the plate, they will take it. He or she will take it, and then they will eat some spaghetti. The main problem here is the algorithm that we would like to allow the philosophers to eat must satisfy mutual exclusion, means that no 2 philosophers can use the same fork at the same time, while avoiding deadlock and starvation. In this case, we would like to provide a solution to this problem. So the main problem is we would like to provide synchronization to help the 5 philosophers to eat their spaghetti such that no 2 philosophers can use the same fork at the same time, while we try hard to avoid both the deadlock and starvation. This problem actually may not seem important or even relevant in itself. However, it does illustrate basic problem in deadlock and even starvation. Furthermore, attempts to develop solutions would reveal many of the difficulties in concurrent programming. In addition, the dining philosopher problem can be seen as a good representative of problems that would deal with the coordination of shared resources, which may occur when an application includes concurrent threads of execution. That means this problem is a standard test case for evaluating approaches that would require to be synchronized. So in the following figure, the pseudocode here actually would suggest a solution, and the solution is using semaphore. This is the first solution, such that each philosopher will pick up first the fork on the left, and then the fork on the right. After the philosopher is finished eating, so that's where they will do the eating part, the 2 forks are replaced on the table. So we start waiting on the Each other philosopher who would like to use the same left fork will wait for it. If there's another philosopher who would like to use the right fork, they will wait for it. And then that philosopher who has initiated the wait responses will start eating immediately. And once he or she is done from eating spaghetti, they will relieve the left fork and the right fork. That means the two forks will be back or replaced back on the table. This solution actually leads to a deadlock because if all of the philosophers are hungry at the same time, they all sit down. They will all pick up the fork on their left, and also they will all reach out for the fork on the right, which is not there. In this position, all the philosophers will starve. So, as a matter of fact, this solution would cause a starvation to the philosophers. To overcome the risk of deadlock here, we could actually buy 5 additional forks. That means we add more resources. Or teach the philosophers to eat spaghetti with one fork. Might be a solution. Or we could even consider adding an attendant who only allows 4 philosophers at a time into the dining table, with at most 4 seated philosophers. That means at least one philosopher will have access to the 2 forks. So with this solution, it looks like it's not working because it causes a big problem of starvation. So if we now look to a second solution to the same problem, and we can see that this solution is free of deadlock and starvation, because we actually ask the philosophers to wait to have some time to think, and then they will be weighted or placed in a room first, and then they will be released from the room one at a time, such that after they have been released from the room, they will start using the left fork and then the right fork. They will eat, and then they will signal out the release of the right and then the left forks, and then the signal out that they are out of the room. So this solution is the second attempt to solve the dining philosopher problem, and it is a successful solution because it avoids both the deadlock and starvation. In the third solution here, we are actually provide a solution to the dining philosopher problem, but not with using semaphores. This one is with using monitors. At this point, a vector of 5 condition variables is defined. We use one condition variable per fork. These condition variables are used to enable a philosopher to wait for the availability of a fork. In addition, there is a Boolean vector that records the availability status of each fork. It will be assigned a value 1, which means the fork is available. A value 0 means that the fork is not available. And then the monitor that we are defining here consists of 2 procedures. The first one is the get forks procedure, which is usually used by the philosopher to seize his or her left and right forks. If either fork is unavailable, the philosopher process is queued on the appropriate condition variable. This enables another philosopher process to enter the monitor. And the released forks procedure, on the other hand, is used to make 2 forks available. You just need to keep in mind that the structure of the solution is similar to that of the semaphore solution that was proposed in the second case that I explained to you, that was in figure 6.12, the second attempt, 6.13. And that means actually 6.12. This one is for the 6.12, which is the first case. In both cases, a philosopher will seize first the left fork and then the right fork. And unlike, however, for the monitor solution, unlike the semaphore solution, this monitor solution does not suffer from the deadlock. So because only one process at a time may be in the monitor, this is the advantage of using monitors. For example, if we assume that the first philosopher process would enter the monitor, and this is guaranteed. So it can pick up the right fork after it picks up the left fork, and this before even the next philosopher would be granted the right chance to seize its left fork. Um, and at this point, we don't have a high chance of deadlock. So as you can see here, there are different solutions to the synchronization problem. The Dynamic Philosopher problem is a case study that is commonly used to address both the concurrency, synchronization, mutual exclusion, and problems associated with mutual exclusion and synchronization for concurrent processes as deadlock and starvation, and how you could provide different solutions to the same problem by the alternative solutions that we have discussed before. And particularly, you could even use the hardware support to enable a solution for this by using special machine instructions, which is faster than enabling software approaches or even plug in within the programming language as semaphores and monitors. So far, we talked about the concurrency fundamentals, mutual exclusion as a major synchronization solutions to concurrent processes, as well as the major problems that may arise with concurrency as deadlock and starvation. Different case studies, including the producer's consumer's problem and the read and write problem, and even the dining philosopher problem. Let's now see the application of what we have learned, like the theory of what we have learned in different operating systems, starting by Unix. So Unix actually, as an operating system, provides a variety of mechanisms for inter-process communication and synchronization. Here we look at the most important of these, including pipes, messages, shared memory, semaphores, and signals. So you can see here that Unix, they use messages and they use semaphores, which we have learned before. For pipes and messages and even shared memory, like the first three categories over here, they can be used to communicate data between processes, while semaphores and signals are used to trigger actions by other processes. Let's start the first one, which is pipes. One of the most significant contributions of Unix is the development of, to the operating system development is the pipe, which was inspired actually by the concept of coroutines. A pipe is defined as a circular buffer. So like this is what the pipe is all about, which allow two processes to communicate on similar fashion as the producer and consumer model that we have addressed before. Keep in mind that this is a first in, first out queue written by one process and also read by another process. When a pipe is created, it is given a fixed size in bytes. When a process attempts to write into the pipe, the write request is immediately executed if there is sufficient room. Otherwise, the process is blocked. Similarly, a reading process is blocked if it attempts to read more bytes than are currently in the pipe. Otherwise, the read request is immediately executed, and the operating system enforces mutual exclusion at this point. That is, only one process can access a pipe at a time. There are two types of pipes in the Unix operating system. The first one is called named pipe, and the second one is unnamed pipe. Only related processes can share unnamed pipes, while either related or unrelated processes can share named pipes. The second one is messages. A message in Unix operating system is considered as a block of bytes with an accompanying type. Keep in mind that Unix provides message send and message receive system calls for processes to engage in message passing. Associated with each process is a message queue, which functions like a mailbox that we addressed before. The message sender at this point would specify the type of the message with each message sent. And this can be used as a selection criterion by the receiver. The receiver, on the other hand, can either retrieve messages in first out order or by type or by the type. A process will block when trying to send a message to a full queue. A process will also block when trying to read from an empty queue. If a process attempts to read a message of a certain type, and this process fails because no messages of that type is present, so the process is not blocked. The fastest form of inter-process communication provided in Unix is the shared memory. This is a common block of virtual memory shared by multiple processes, such that processes read and write shared memory using the same machine instructions. They used to read and write other portions of their virtual memory space. Permission is read only, or even write for a process. It is determined on a paired process basis, and also the mutual exclusion constraints are not part of the shared memory facility, but must be provided by the processes during the shared memory. During the shared memory usages, or like using the shared memory. Semaphores in Unix is more or less system calls. So the semaphore system calls in Unix system are a generalization of what we have addressed before, like the function same weight and same signal primitives that we discussed even in chapter 5, where several operations can be performed simultaneously, and the increment and the decrement operations can be values greater than 1. The kernel does all of the requested operations atomically. No other process may access the semaphore until all the operations have been completed. Just keep in mind that a semaphore consists of the following elements: the current values of the semaphore, the process ID of the last process to operate on the semaphore, number of processes awaiting for the semaphore value to be greater than its current value, and number of processes waiting for the semaphore value to be 0. And also, it should be noted that associated with the semaphores are queues of processes blocked on that semaphore. Semaphores are actually created in sets, where a semaphore set consisting of one or more semaphores. There is a system called SAMCTL that allows all of the semaphore values in the set to be set at the same time. In addition, there is the SEM operation, SEM operation, another system call that takes an argument, which is a list of semaphore operations, each defined on one of the semaphores in the set. And when this system call is made, the kernel will perform the indicated operations at one at a time. For each operation, the call function is specified by a value given by the SEM operation system call. For signals, a signal is defined as a software mechanism that informs a process of the occurrence of an asynchronous event. A signal is similar to a hardware interrupt, but does not actually employ priorities. That is, all signals are treated equally. Signals that occur at the same time are presented to a process one at a time with no particular ordering. Processes may send each other signals, or the kernel may send signals internally. A signal is delivered by updating a field in the process table for the process to which the signal is being sent. Because each signal is maintained as a single bit, signals of a given type cannot be queued. A signal is processed just after the process wakes up to run, or whenever the process is preparing to return from a system call. A process may respond to a signal by performing some default action, like termination, as an example, or executing a signal handler function, or even ignoring the signal. As you can see over here in the following table, we have different type of signals for the Unix SVR4 operating system, and the description of each signal is given. So you can see we have 19 signals. Each one has a value between 0 and 19, and then between 1 and 19. And we do have the name of each signal and the description for each signal. For example, the signal SIG IoT refers to IoT instruction. The SIG EMT refers to EMT instruction. So as you can see, Unix allows signals to provide synchronization and concurrency handling in its own multi-processing and multitasking and multi-threading platform. Now, if we're going to talk about a special case for Unix, which is Linux, and we'd like to address the Linux concurrency mechanism, it also handles signals, but different in a different fashion as compared to Unix, such that Linux includes all of the concurrency mechanisms that found in Unix systems, including pipes, messages, shared memory, and even signals, as I said. But Linux supports a special type of signal, not like the general signals that we talked about it for Unix. Now, for Linux, it supports a special type of signals. These signals are called real-time signals, or like RT signals. These are part of the Linux operating system, especially those signals that have different characteristics, including signal delivery will be done in priority order. And multiple signals also can be queued. So if you have multiple signals of different types, those signals could be queued. And with the standard signals, no value or message can be sent to target process. It is only a notification. With RT signals, it is possible to send a value. It could be like an integer or even a pointer along with the signal. Also with the RT signals, it is possible to send a value, as I said, with the signals. It could be a pointer, it could be an address, or it could be even an integer. Keep in mind that Linux also includes a larger set of concurrency mechanisms, especially intended for use when a thread is executing in a kernel mode. That is the point where these mechanisms are used within the kernel. And the main reason for using those synchronization mechanisms is to prevent concurrency, not only in the user mode, but also in the kernel mode. Linux, on the other hand, provides a set of operations that guarantee atomic operation on a variable. These operations can be used to avoid sample race conditions. An atomic operation would execute without interruption and without interference. On a uniprocessor system, a thread performing an atomic operation cannot be interrupted once the operation has started until the operation is actually completed. In addition, on a multiprocessor system, the variable being operated on this system is locked from access by other threads until this operation is completed. There are two types of atomic operations that we can see in Linux. The first one is integer operations. The second one is bitmap operations. For integer operations means those atomic operations that works on integer variables, and they are typically used to implement counters. For the bitmap atomic operations, they operate on one of the sequence of bits at arbitrary memory locations, which is included by a pointer variable. So as you can see, and we explained, the two types of the atomic operations are the integer atomic operations and the atomic, the bitmap operations. For integer operations, as I said before, it operates on integer variables, and the bitmap operations operate on 1 bit in a bitmap. These operations actually must be implemented on any architecture that would implement Linux. Keep in mind that for some architectures, there are considering assembly language instructions for the atomic operations. And on other architectures, an operation that locks the memory bus is used to guarantee that the operation is atomic. I don't want you to memorize any of the notations for those atomic operations, but I just wanted you to know that for atomic operations in Linux, they are classified into either integer operations, which operate on integer variables, and bitmap operations that would operate on a bit, just 1 bit in a bitmap. The most common technique used for protecting a critical section in Linux is the spin lock. Only one thread at a time can acquire a spin lock. Any other thread attempting to acquire the same lock will keep trying. It means spinning until it can acquire the lock. In essence, you need to know that a spin lock is built on an integer location in memory that is checked by each thread before it even enters its critical section. If the value of if the value is 0 of this integer location, that means the thread sets the value to 1 and then enters its critical section. If the value is non-zero, the thread continually checks the value until it is 0. And the phenomenon of spin lock is easy to implement, but has the disadvantage that lockout threads continue to execute in a busy waiting mode. Thus, spin locks are more effective in situations where the wait time for acquiring a lock is expected to be very short. That means it could be just less than 2 context changes, so it won't take them much long time. The basic spin lock, which is the main thread we see in the spin locking phenomenon, as opposed to the read-write spin lock, which has been explained in previous classes, is this basic spin lock is very similar to the read-writing spin lock that we talked before. However, for the plain lock, is used if the programmer knows that the protected data is not accessed by an interrupt handler or even bottom half of an interrupt handler. And the appropriate non-plain spin lock is used in many applications. And as you can see here, we have the spin lock, we do have the irregular bin lock, and we have the irregular safe bin locks. Like we do have a lot of spin locks operations that are maintained by Linux. Again, I don't want you to memorize any of these spin locks. Just keep in mind that spin locks are the most common way of protecting a critical section in Linux, and it is commonly used. Just like it causes a trouble with the busy waiting mode that is being initiated with the spin lock, but it has been used a lot in Linux. So moving from the spin locks to semaphores, which we have talked about it a lot in fundamental theory related to solutions to deadlock and even starvation. At the user level, Linux actually provides a semaphore interface corresponding to that in Unix. Internally, Linux provides an implementation of the semaphore for its own use, which is a code that is part of the kernel, which would invoke kernel semaphores. These kernel semaphores cannot be accessed directly by the user program. It has to be accessed by system calls. These semaphores are implemented as part of functions within the kernel and are thus more efficient than even user visible semaphores. Linux would provide 3 types of semaphore facility in the kernel. So we're talking about kernel semaphores. We are not talking about the user visible semaphores, which is commonly used a lot in Linux to support concurrency. The 3 types of kernel semaphores are binary semaphores, counting semaphores, and reader-writer semaphore. So again, in the following table, you will see different type of semaphores and different type of accessibility of using those semaphores through functions like kernel functions. Those functionality will allow the usage of traditional semaphores versus reader-writer semaphores. Each one of those functions will perform a certain task to either access traditional or general or counting semaphores, or they will use the concept of the reader writing with the fact of allowing semaphores to be accessed either one semaphore or multiple semaphores. So to enforce actually the order in which instructions are executed in Linux, and to allow the different operations that would provide a good synchronization between processes, Linux provides what we call the memory barrier operations. In the following table, we can see the most important functions that are defined for this facility. For example, the RMB operation, it ensures that no reads occur across the barrier defined by the place or the location of the function RMB. That means it prevents loads from being reordered across the barrier. Similarly, the WMB operation also ensures that no writes occur across the barrier defined by the place of the WMB in the code. On the other hand, MB operation provides both a load and a store barrier. That means it prevents loads and stores from being reordered across the barriers. There are 2 important points to note about those barrier operations. The first one is the barriers relate to machine instructions, namely loads and store. At this point, the higher level language instruction, for example, equal instruction would involve both a load, which means read from location B from a certain location and store it in another location. Also, one note that I want you to be aware of is the RMB and the WMB, and as well as the MB barrier operations dictate the behavior of both the compiler and the processor. And in the case of the compiler, the barrier operation dictates the compiler not reorder the instructions during the compiler process. While in the case of the processor, the barrier operation dictates that any instructions pending in the pipeline before the barrier must be committed for execution before any instruction encountered after the barrier. So lastly is the read, copy, write, update mechanism. The RCU, the read, copy, update mechanism, is an advanced mechanism, which we call it lightweight synchronization mechanism, which was integrated into Linux in 2002. The RCU is used widely in Linux kernel. For example, in the networking subsystem and the memory subsystem, the virtual file system, and even more. The RCU is used by other operating systems, and even they are considered as a user space. Its library is considered as a user space RCU library underneath different libraries in the operating system. This library is called library URCU. As opposed to common Linux synchronization mechanisms, RCU readers